welcome Dunal Hernan.
Hello everyone, welcome to the Hamming Innovation Hall here at Nokia Bell Labs. It's great to have all of you here for the second in our Shannon Luminary lecture series. This is very exciting for us. Today in this, our company, we have a number of our academic collaborators. We have 50 STEM students. We have our experiments in arts and technology collaborators. We have our internal staff from the different business functions on Nokia on site, and we have our global sites viewing this live as well. So this is a really exciting time for us to be able to share with this lecture globally. So just before we get started, I'll do some boring housekeeping before we get to the exciting lecture. So we have fire exits left and right of the stage, and as you enter the building. We have restrooms at the front of the building also. And what we will do is we will ask everyone to please ensure you silence or turn off your phones out of respect for the speaker and also for your fellow colleagues here in the room. So what we're going to get going, just to give you a sense of the outline, we're going to have Marcus Weldon come up and introduce the speaker. We'll have questions and answers at the end, and we will invite some of you former colleagues and collaborators to come down and say hello to Yann, and we also have some drinks and snacks out the front of the building also. So with that, I'd like to introduce Marcus Weldon, the president of Bell Labs, and the CTO of Nokia, to introduce Yann LeCun.
Hi everyone. It's a fantastic honor to have Yann here. It turns out we are more similar than not. Not only because we're made from the same sort of biological systems that Yann is quickly going to turn into intelligent machine systems, but Yann joined Bell Labs around the time actually he left Bell Labs around the time I joined, and that's no coincidence either. Unfortunately, it's happened multiple times. A previous Nobel Prize winner was called a guy called Jay Troutman. Similarly, left about a year after I joined, and so I like to think I was the end of one of the great eras of Bell Labs, but hopefully this is a signature that he's deigned to come back, and this is the beginning of one of the next great eras of Bell Labs. But all joking aside, it is a privilege to have Yann here. Not only is he the founder or father of convolutional neural networks, sort of vision-based learning systems, which he's going to talk about, and the evolution of those to be predictive systems, which is a fascinating topic. But he's a thoroughly good guy. And it turns out, I looked on his website, and I recommend you go there because it's very humorous. There's a lovely aspect to it, but there's a not-so-serious part to it, so I'm going to read you some of the not-so-serious parts. One is, back to the comment I made about him being a good guy, it turns out that's his name. LeCun, which, and I know I have to either nasal or not nasal it, depending on whether it's, I do the full Breton pronunciation because he's from Brittany, is roughly derived from LeCunf, which means nice guy. So that is one of the facts there. But he's got some beautiful quotes there that I love because they're so sort of classically Bell Labs, in that they're quirky, geeky, but really funny. And so here's one, and this is very relevant to this talk. It says, even the smartest people think that they are not smart enough to understand the meaning of life, the universe, and everything. Yet many not so smart people think they are smart enough to do so. And I think there couldn't be a more relevant comment than that at this point in time. And of course, because he's one of us, he goes on to say, and they don't know the answer is 42. And if you don't know what that refers to, then you should. He also goes on to say he loves Tex Avery, the cartoonist, and that cartoons and animation are one of the highest forms of art. In fact, one of the only good forms of art coming out of the US, other than jazz. That's not true. He didn't quite say it that way, but that was fascinating. But here's another one. This is a great one. Fear of lawsuits will drive people to write sentences with provably zero information content. Isn't that wonderful? But enough of my silliness. I will simply say that it's a great honor to have Yann here. He's really he has become the father of sort of AI, not only in Facebook, but probably globally, working with his collaborators. He was at Bell Labs from 88 to 96, then went to AT&T Labs and worked in Larry Rabina's organization for about 5-6 years, then to NEC, then to NYU, and then got recruited by none other than Mark Zuckerberg himself. That's the level of which Yann's renown had risen. So he's now director of AI at Facebook, quite a large team there, and he's going to tell you about his view of whether, at least this is my view of his talk, whether in fact machines will be able to emulate humans and be able to predict futures. So without further ado, I'm going to welcome Yann LeCun to the stage.
Well, thank you for coming so numerous. It's really a pleasure to be here again. After so many years. So I actually have a similar story to you. When I interviewed at Bell Labs in Homedale, I visited Steve Chu's lab, and I was incredibly impressed and said, I'm gonna have to join this. This is amazing. I wanted to go back to France. My wife wanted to go back to France, but I said, just told my wife, not a problem. We're gonna live in New Jersey, but it's just gonna be for a year or two. It's been 28 years, but by the time I arrived at Bell Labs, Steve Chu had left. Okay, so I'm going to talk about, I guess, what I call predictive learning. Other people in the community may call this something else, unsupervised learning, perhaps. But before, I'm going to talk a little bit about kind of the past, recent history, or old history of neural nets. So I actually I have a couple pieces of Bell Labs memorabilia. So I joined Bell Labs in 1988 and stayed with AT&T at the time of divestiture when Lucent Technologies was spun off. And the group I joined was led by Larry Jackal, and it was in the electronics lab in Homedale, and they were interested in fabricating neural nets. And what you see in the picture on the left here is actually one of the first kind of hardware neural nets. It's a resistor matrix. They invented some new technology to kind of make very, very small resistors. And then, this was before I joined the lab, and then they kind of tried to figure out, they got the idea of this from John Hopfield, who was a famous biophysicist who had a gig at Bell Labs. And Larry went to see him and ask him, I have a new department, I'm not sure what to do, what should I work on? He said, well, there's this neural net thing, you should probably look at this. So they started building Hopfield nets out of silicon, essentially. Silicon and kind of exotic sauces to make the resistors. And then realized that there's two problems. First of all, you have to build amplifiers you have to put around this matrix, and the amplifiers are about 10 times bigger than the resistors. And the second thing is that you have to talk to computers, and then you have to go through converters and everything. So even though you could build those incredibly fast and compact neural nets on the chip, you couldn't really talk to them. You couldn't really use them. But it was sort of a really exciting period at the time. This is Larry Jackal here at the top. This is around 1994, I believe. We were actually on a sailing trip in the Virgin Islands. And a few years later, we had kind of a lab reunion. You see some people here, the guy with the white shirt is a character. His name is John Denker. He was at Homedale, but he had an office in Murray Hill here that he shared in the biophysics lab. I think he was in Horst Stormer's organization at the time. And he was sharing the office with Wilfried Denk, who is now at Max Planck Institute. And so there were the two names on the door, Wilfried Denk, John Denker, and someone wrote below, Denkest. Okay, so a lot of pretty much all the applications that you hear about of AI and machine learning use a mode of learning called supervised learning. So supervised learning is kind of like showing a picture book to a child. You want to train a machine, for example, to recognize images, to classify images of cars and airplanes. And you show a car to the machine, and the machine has kind of adjustable knobs on it that basically determine the input-output function that the machine computes. And what you want is you want the red light to turn on when you show a car, and you want the green light to turn on when you show an airplane. And so what you do is you show an image of a car, and then you kind of twiddle the knobs a little bit so that the brightness of the red light goes up and the brightness of green light goes down. And then you do the reverse when you show an image of a plane. And if the machine is built in such a way that it has enough capacity, if it's powerful enough, and you kind of keep adjusting those knobs just a little bit for every thousands or millions of samples, eventually it will figure out what really is the essence of the difference between those two things. That's pretty much as simple as that. So if you want to formulate this in a mathematical term, you're kind of minimizing some sort of objective function that measures the discrepancy between the output you want and the output you get that the machine produces, average over a number of training samples, and you minimize this loss function with respect to all the knobs in the machine. Now, in a real machine, a typical application of machine learning today, you may have hundreds of millions of those knobs, and of course you need efficient ways to figure out in which directions to turn them, which I'll talk about later. And this is the first machine that was capable of learning, called the perceptron. It was built by Frank Rosenblatt and his team at Cornell. And it was an analog computer. So there was sort of a retina, which is sort of an array of photoreceptors. And what you see in the middle here is what we would now call a feature extractor. It looks like a spaghetti plate, really. And the usual joke I say is that now we replace this with spaghetti code. And then at the right is the classifier. So that's the part that is actually trainable. And so the classifier does a very simple thing. It takes the series of outputs that comes out of the feature extractor. It's a vector. And it computes a weighted sum of the components of that vector. Basically, it computes the dot product between the vector and a vector of weights. If that dot product is larger than the threshold, it's category A. If it's smaller than the threshold, it's not category A. Okay? Or category C in that case. And so the way the system was implemented, the weights here, what you see Frank Rosenblatt holding is a bank of 8 weights, and each weight is actually a potentiometer with a motor on it. And so to train the machine, you show a sample, then you press a button, and all the motors go. And depending on how long you press, they will turn more or less, essentially. And that's how you adjust the step size in the gradient descent algorithm, essentially. And so only a couple of years later, it became practical to really kind of write programs to do this, and right now, those algorithms are still used. The perceptron learning algorithm is still used, and basically now it's a 3-line Python script. But that was kind of the first interesting kind of learning machine. There were other attempts at IBM for training a machine to play chess, for example, that use a slightly different principle. And I learned about this when I was an undergrad, and I was absolutely fascinated. This was in the early 80s, 1981 or so, and I'd never heard of the possibility of a learning machine before, and that's what got me hooked into this kind of thing, and I realized nobody was working on this at the time. This had fallen out of fashion. Essentially, the field had died in 1969 after a book was published that proved there was dire limitations of those models. And so nobody was working on this at the time. But really, the problem that these guys were trying to solve, and the problem that essentially got solved to some extent in the mid-80s, and I had a little bit to do with this, is the problem of not training a machine with a single layer, but training a machine with multiple layers. And that's really what deep learning is about. So what you see here is, at the top is the classical way of doing pattern recognition, classical, which means classical way until about 5 years ago. And at the bottom is kind of the deep learning way of doing pattern recognition now, where supervised pattern recognition in particular, where you have an image at the bottom, and the machine is composed of a cascade of modules, all of which are parametrized, have knobs on them, and you train the entire machine end-to-end to basically optimize your objective function, compute the right answer. And what's magical about machine learning in general, there's a lot of theory on this, is that you train on a particular set of training samples, and the machine generally works pretty well on new examples it's never seen before, as long as they are sufficiently similar to the example it's been trained on. So people back in the 50s and 60s were really kind of looking for algorithms to be able to train multi-layer systems of this type, but really couldn't quite figure it out. And the reason was because the mindset was hooked on using binary threshold units. And if you use binary threshold units and kind of, logic a little bit, you don't get the idea that you have this sort of continuous function that you can adjust, and you can compute gradients and adjust knobs so as to minimize an objective function. And so it took until the mid-'80s for people to change the type of units in those neural nets to use continuous functions, which kind of immediately suggested the idea that we should just use gradient descent, essentially, to compute those. So here's what a modern neural net looks like. And there was a wave of interest in those models starting around 1986 or so, and it kind of died. It lasted for a little less than 10 years, and the sort of interest died in the 90s. And it's because, partly, it's not entirely clear why, but it's partly because those systems tend to be very, very finicky. It's very hard to make them work. There's a lot of black art in it. And at the time, it was difficult to distribute your code. Now it's kind of commonplace to kind of distribute your code in open source. Everybody used the same platform, etc. But back in the 90s, it just wasn't the case. And so the field died a little bit because of that, and because the more classical methods seemed to work for the size of data sets that were available at the time. But here is what a modern neural net looks like. So it's a succession of two types of operators. You take an input, you represent it as a vector or as a multidimensional array, basically just a table of numbers. And then you're going to take this, multiply it by a matrix. The coefficient in the matrix are the adjustable knobs. And then you take the resulting vector and apply a pointwise nonlinearity to all the components of that vector. So for example, a typical nonlinearity that people use nowadays is what we call the ReLU. It's really the half-wave rectifier. It's the positive part of an argument. And so that's a very elementary function, parameterized linear transform, then pointwise nonlinearity, and then you stack multiple layers of that. And you can show that a lot of functions can be approximated as close as you want with this kind of architecture. You only need 2 layers, but you might need a very, very wide middle layer. And things become more efficient as you stack more layers. You end up being able to compute more functions with kind of fewer nodes. So then the next question is, how do you adjust the knobs? How do you adjust the coefficients inside this? And that's done with what's called the back-propagation algorithm, which is an extremely sophisticated mathematical concept. It's basically chain rule. That's what it comes down to. Leibniz could have figured it out. Actually, he figured it out. So that goes back a long time. But the realization that you could use essentially chain rule to compute the gradients with respect to all the parameters in the system to do machine learning basically wasn't really sort of commonplace until around 1986 or so. It took a very long time for people to believe in the fact that it could work. There were papers in the 50s by Marvin Minsky and others who said that this idea of doing gradient descent, or hill climbing, they called it, is never going to work because the complex systems are going to be trapped in local minima. And so there was this mindset that somehow, because those systems are complex, the local minima problem would be fatal. It turned out that's not true. So the idea of backprop is when you have a system that's kind of a cascade of modules this way, you put an input, you propagate forward, you compute the value of the cost function that measures the discrepancy between what you want and what the machine produces. And then there is sort of a backward signal that goes from the top to the bottom that kind of propagates the gradients, if you want, and that's what is called backpropagation. Old idea became popularized around 1986. I had a version of it in 1984, but the main version was popularized by Dave Romerhart, Jeff Hinton, and Ron Williams around 1986. Okay, then the next question you have to figure out is what do you put in those boxes? So you can, it's fine to think about multiplying a vector by a matrix, but when the input to the system is an image, say a few hundred pixels by a few hundred pixels, okay? So let's say 200 by 200 pixels. So that means you have 40,000 input variables times 3 if you have color. 120,000 input variables. So now you're going to multiply this by 120,000 by 120,000 matrix, and that's just not going to be practical. So you have to kind of think about how to specialize those linear operators to make them practical. And in the case of images, one answer to this is convolutional neural networks invented at Bell Labs around 1988. I actually started working on this when I was a postdoc in Toronto, just before joining Bell Labs. But it's really at Bell Labs where I was able to kind of make this work. I was amazed, actually. A few months before I joined Bell Labs, Larry calls me up and says, we'd like to buy a computer before you come, so it's ready when you come. What would you like? I said, well, here in Toronto, we have a Sun 4. Do you guys have a Sun 4? I said, no, we don't, but we can buy one before you come. And the Sun 4 in Toronto was shared by the entire department, 30 people. And when I come to Bell Labs, I had a Sun 4 for me, just for me. I said, what's going on? He said, well, here you don't get famous by saving money. And so we needed those machines to run those things. And so the idea of convolutional nets is that you basically, instead of having a general matrix that you multiply the input vector by, you view the image, the input as a 2D array, really. And the linear operator you're going to apply is going to be a convolution. So I'm sure there's a lot of people here who know what a convolution is. Of all audiences, when I talk to computer scientists, I actually have to explain what a convolution is. But so here, what I mean by this is kind of a discrete operation where you take the input image, you take a neighborhood in the input image, say 5 by 5 in this case, and you compute the dot product of the pixels within this small neighborhood of 5 by 5 with a set of weights, 25 weights. And that gives you a weighted sum. You compare this to a threshold or pass that through a nonlinearity, and put the result in the output map. And then you take this little neighborhood and you swipe it over the entire image using the same weights all over, which is why it's a convolution operation, a discrete convolution in this case, and that gives you the result here, the output map. So the idea of convolutional net is the first layer is basically a bunch of convolutional filters like this applied to the image, each of which detects a particular type of feature or motif all over the image, and kind of turns on or turns off depending on whether the local motif matches the weight patterns. The weights, of course, are learned. You can compute the gradient of some objective function with respect to them using back-propagation, no problem with that. Then the next layer up is what's called a pooling operation. So the role of pooling is to aggregate the output of each filter over a small area. And the purpose of this is to build a little bit of shift and distortion invariance into the system. And I'll come back to this in a bit. And all of those ideas, actually, I was inspired by classic work in neuroscience for this, as well as some work by a gentleman called Kuniko Fukushima, no relationship with the nuclear power plant, who came up with a model called the neocognitron, which had this idea of filters that you replicate and kind of pooling operations, which were inspired by neuroscience, classic work in neuroscience from the 60s, Nobel Prize-winning classic work, and kind of built a simulator for it, if you want, but it didn't have backprop, so we couldn't really train it properly. And the idea of ConvNets is that you kind of stack multiple stages, which are those successions of filter bank convolutions, nonlinearity, and then pooling operation, and then you repeat the process, filter bank, nonlinearity, pooling, etc. So here is one of those things in action. This is actually a vintage convolutional net from Bell Labs many years ago. Has been trained to recognize handwritten digits, and you see the input, the first layer, which is composed of those feature maps, then the second layer after pooling, and whenever the input shifts by 2 pixels, then that, after pooling, the shift is only 1 pixel, and the reason is that this pooling operation essentially reduces the spatial resolution of the image. It aggregates the response of the filters over a 2x2 region, and then you step the window over which you do this aggregation by 2 pixels. And then the next layer up is, again, a set of convolutions. Each of those maps actually applies different convolution kernels to each of the feature maps on the previous layer, add the result, and then pass that through a nonlinearity. You have pooling again, and then convolutions again, and then the output layer is not shown here. Here's an example where we show the output layer. So this one has been trained to not just recognize a single character, but kind of a string of characters, which was really the first time that people could use learning techniques basically or any technique in fact, to simultaneously segment and recognize multiple objects. So what's interesting about convolutional nets is that they don't just learn, or deep learning in general, is that they don't just learn a classification function, they learn to represent the perceptual world. They sort of learn to extract the features in the image that are relevant for the task that we're talking about. This is a fun video that is from 1992 or 1993. It's a demo of one of the first prototype systems that we had. This is actually my phone number in Homedale, New Jersey, at Bell Labs, no longer operating. So I hit a key, and there's a video camera that grabs the image, and it goes to this 386 PC that recognizes each of those characters. This is actually running not on the 386, but on an AT&T DSP32C, for those of you who are old enough to remember what that means, capable of the blazing speed of 20 megaflops. And we really needed this kind of power at the time, which was really extraordinary to be able to run those systems. It was very robust. I mean, there was really no other system in the world at the time that could kind of deal with this sort of complicated shapes. This is Donnie Henderson is one of the lab engineers, and this is Rich Howard. I'm sure a lot of you know Rich Howard, right? Okay, because he, retired from Lucent a few years ago. He was my boss's boss. He was the lab director. Wonderful guy. That actually gathered a little bit of press at some point in the New York Times, and eventually we managed to hook up with a development group at Bell Labs that developed a check reading system that was deployed around 1995 for various applications. It was actually really kind of well deployed in 1996. We actually had a party at a fancy restaurant near Homedale to celebrate the fact that our check recognition system had been fielded, essentially. And we came back to the lab after lunch, and we saw everybody kind of making funny faces. This was the day that the split of the company was announced. Then there is an interesting story, which is that the product group that was working on this was at NCR, which at the time was part of AT&T. The development group, of course, was working together with us. But when the company split, all the researchers went to AT&T. It's because the president of Bell Labs at the time hated this stuff. So every machine learning people went to AT&T. That's why there was no machine learning at Bell Labs for a while. The development group, the engineering group that was working on this, stayed with Lucent. They weren't given a choice. And the product group went with NCR. And the lawyers, in their infinite wisdom, gave all the patents to NCR, which had no idea what they had. Thankfully, those patents are expired. But not everybody was convinced. So even within our lab, so there was this guy in the lab, Vladimir Vapnik. He's an extremely famous person in machine learning. And he kind of basically came up with a whole theory of machine learning, the most general approach to learning theory. And he was really not convinced that this was the ultimate answer to learning. He really didn't believe in the concept of neural nets. And so Larry, and he was working in the same lab, so he is the inventor of support vector machines, if you know what that is, and kernel machines. And we were, 2 offices from each other. So convolutional nets and support vector machines were invented 2 years away from each other, 2 offices away from each other. SVMs became kind of the dominant model for about 10 years in machine learning until relatively recently. And so Larry Jackal and Vladimir had a bet in 1995. Jackal bet one fancy dinner that by March 14, 2000, people will understand quantitatively why big neural nets are working on large databases. Working on large databases are not so bad. Which means understanding theoretically, using bounds and theory, etc. Vapnik bets one fancy dinner that Jackal is wrong. But if Vapnik is the person figuring out the bounds and conditions, then Vapnik still wins. So, so this was a disguised incentive that Larry designed to kind of tell Vladimir, you should work on this. And Vladimir lost. By 2000, people were still using neural nets, although it was not as popular as 5 years earlier. And there was a second bet. Vapnik bets one fancy dinner that by March 14, 2005, no one in their right mind will use neural nets that are essentially like the ones used in 1995. And Jackal bets that Vapnik is wrong, signed by Vapnik, Larry Jackal, and me. Vapnik kind of lost that one too. I'm sorry. Larry Jackal lost the first one, so it was never really proved why neural net works so well. But he won the second one, and so they kind of split the bill at the end, because they waited until 2005. And this is a picture of the dinner in 2005. The person on the left here is Léon Bottou, who is has been a long-time collaborator of mine and is actually at Facebook as well. So fast forward about 10 years, and around 2013, 2012, 2013, people figured out how to run very, very large convolutional nets on very large data sets using GPUs. GPUs were basically the only way to get cheap, access to kind of a cheap supercomputer if you want. You could have, a teraflop or so in a machine, and you could stack multiple cards and get, a few teraflop of computation. That allowed people to run very large convolutional net. And I wish my lab at NYU had been the first to do this, but it wasn't. It was our friends at University of Toronto in Jeff Hinton's group, where I'd done my postdoc many years before. And so they spent a lot of effort trying to kind of optimize those things on GPUs and trained on a newly available data set called ImageNet, which had 1 million training samples. And it worked beautifully, so much, so nicely, in fact, that they won a competition called the ImageNet competition for object recognition. 1 million training samples, 1,000 categories of everyday objects. And they won it by such a margin that the computer vision community, which so far had been extremely kind of skeptical about deep learning and convolutional nets, basically dropped everything they were doing and switched to using it. The difference was so large. So the previous state of the art was around 26% error by some measure, and they got 15%. And the 26%, it was clear that the previous methods were kind of saturating. So it created a revolution in image recognition in computer vision, where until 2011, 2012, you would submit a paper to a computer vision conference, and it would be soundly rejected by people who would say, what the hell is a convolutional net? And by 2015, you cannot get a paper accepted at any vision conference unless you're using convolutional nets. A similar revolution occurred in speech recognition a couple of years earlier, which our friends in Toronto also had a lot to do with. So what's interesting about convolutional nets is that they kind of learn a sort of compositional, hierarchical representation of the world. Elementary images, you could think of them as being compositional in the way that, in the sense that images are composed of elementary motifs, like oriented edges, and then combinations of edges form simple shapes, things like corners and circles and gratings and things like that. And then combinations of those form kind of more complex shapes, like parts of objects. Combination of those form objects. And the multiple layers basically end up kind of learning those detectors at the various levels. So those are visualizations done by my colleague Rob Fergus at the time at NYU, now at Facebook as well. He's still part-time at NYU, where they kind of visualize the type of shape that would maximally activate a particular unit in a layer within the convolutional net. And the reason this works is because the world is compositional, essentially. I'm sure there's lots of physicists in the room, and of course, all the physics is based on the idea that particles assemble to form bigger particles, and particles assemble to form atoms, and atoms form to form molecules, etc. The world is compositional, but the visual world is also compositional. There's a nice quote from a colleague at Johns Hopkins, Jason Eisner, who says, it's basically a play on one of Einstein's famous quote, which is, what's the most incomprehensible thing about the world is that it is comprehensible. And it's probably because it's compositional. So his form of it is, the world is compositional, or there is a God. slightly obnoxious. So over the last 3 or 4 years since this revolution occurred, there's been a lot of really smart people kind of coming to the field and coming up with really new ideas and surprising even me on how well those things can work. So there's been in particular an inflation in the number of layers that those neural nets have nowadays. At the top, the top two systems, VGG, which is from Oxford, and Google Net, which is from Google, have something like 20 or 30 layers, and they were proposed around 2014 or 15. And at the bottom, you have a new form of neural net called ResNet, that means residual networks. This was proposed by a gentleman called Kai-Ming He, who at the time was at Microsoft Research Asia. This is just a year and a half ago or so, 2 years ago. And this works amazingly well. The basic idea behind ResNet is that by default, every layer is basically the identity function, and what the neural net itself is computing is a deviation of the function you want to compute with respect to the identity function. And it turns out it can be built in some sort of fail-safe mechanism that makes the system survive having many, many layers. And so modern convolutional nets have anywhere between 50 and 100 layers using this kind of trick. Kai-Ming He now works at Facebook. So convolutional nets have been applied to all kinds of different things. This is an application. So if you are on Facebook and you upload a picture of your friends are tagged automatically, and the face recognition system uses a convolutional net. In fact, every photo uploaded on Facebook goes through 3 convolutional nets. And so one convolutional net is used to recognize faces. Another one is used to essentially recognize all the objects in the image and tags and et cetera. This is used for kind of ranking the image in your newsfeed. And the third one is to detect objectionable content, essentially. And you realize there is kind of a slight problem with scale when you learn that people upload on the order of 1 billion to 1.5 billion photos on Facebook every day. So we're burning a lot of cycles and a lot of megawatts into running convolutional nets. I know there are kind of, ASIC designers in the room here. I think you do a lot of good in the world if you have some way of computing those things really cheaply in terms of power. Because it's going to get worse. We're going to apply this to video. Those networks are going to be everywhere in your car, in vacuum cleaner. So a few years ago, about 10 years ago, there was a DARPA program called LAGR, which means Learning Applied to Ground Robots, where the idea was to use machine learning to kind of see if a robot could be trained to drive itself in nature, off-road robot. And what we used there was a convolutional net that is basically applied with a sliding window over an entire image and then classifies every window, if you want, in the image as to whether the central pixel is traversable or not, whether the robot can drive over it or not. And the interesting thing about it is that it basically self-trains by getting the information as to whether something is traversable using stereo vision, but that only works at short range. So for long range vision, it's using the convolutional net. So it's been trained, it can label the entire image, and after that, you can test it and have pesky students annoying this poor robot. So they're actually entitled to do this because they are the ones who worked on the project, and they're pretty sure the robot is not going to break their leg because they wrote the code. So this was Raya Hetzel and Pierre Samanet. Raya Hetzel leads the robotics group at DeepMind in London, and Pierre Samanet also works on robotics at Google in California. A consequence of this project is that we eventually figured out how to apply this technique of kind of a sliding window to classify every pixel in an image with the category of the object it belongs to, right? So here the system, this was built around 2009, 2010, the system kind of labels the road, the sidewalk, the cars, the trees, the buildings, the windows, the doors, etc. Pedestrians, you really don't want to miss pedestrians. And this is, it's not perfect. There's been a lot of progress in those kind of techniques in the last few years. It labels the bottom here as desert. which is obviously wrong. This is Washington Square Park in middle Manhattan. There is no beach I'm aware of, and it's certainly not a desert. That's as good as it gets, or as it got back then. And it got, the idea kind of percolated in sort of a number of different circles, particularly people working on self-driving cars. So here what you see is a short video from a company, an Israeli company called Mobileye. It's been around for a while, and they kind of adopted the religion of deep learning a few years ago and kind of retooled the entire system around deep learning, and now that's what they use for their vision system. For a while, they were the providers of vision systems for Tesla. They kind of divorced a year ago, but now Tesla has its own system. Another company that's really kind of gotten into this in a big way is NVIDIA, the GPU manufacturers. And in fact, NVIDIA, if I can get my pointer. So this is a car built by NVIDIA called BB-8, and it is driving itself in kind of fairly weird environments. This is actually in Homedale, in the Bell Labs site in Homedale. This is the parking lot in Homedale, New Jersey, for those of you who've been there before. Right, so this is before training, and that's after training, okay? After a few hours of basically observing a person driving the car around. So it's called imitation learning, which means that there is a convolutional net looking at a picture coming out of the camera, and then learning to predict what the steering angle is going to be of the car. This is not in Homedale. This is in Sandy Hook, I believe, Sandy Hook Park in New Jersey. So works pretty well. They have kind of more recent demos. If you look for autonomous car NVIDIA, you'll see a bunch of videos there that are kind of cool. So a lot of interesting things in this space. More recently, the group I lead at Facebook, so it's kind of the first research lab at Facebook, really, that was created at the beginning of the end of 2013, beginning of 2014. It's now grown to about 90 people, a combination of scientists and engineers. And we're strictly focused on AI, essentially, and trying to kind of push the state of the art forward. So this is a vision system that was built at Facebook that recognizes objects and images, but doesn't just recognize them. It also kind of paints their outline, if you want. So it figures out where objects are. And it's a convolutional net that's been trained to classify objects, but also to generate a mask of the object it's currently recognizing. It's a very complicated combination of convolutional nets of various kinds trained in a very complex way. The code is open source if you are interested in playing with it. It's called Sharp Mask, and it's on GitHub. And it can do things like this. So it will recognize objects and draw the outline of all the objects: person, cell phone, laptop, person, even behind chicken wire, even if you see only the heads. Look at the fuzzy people in the back. This thing can only handle about 80 categories. Broccoli. I actually don't like broccoli, so you can imagine a robot picking up broccoli out of Chinese dishes. And the best application of all this is counting sheep. So if you ask a computer vision researcher 5 years ago, how long is it going to take for us to be able to do this kind of stuff, they would have told you, at least 10 years. And they would have no idea, how to actually do it. And the fact that we can now essentially do this is astonishing, even to me. Okay, so now let me talk about the meat of the subject, if you want, after this long preliminary, which is really what are the obstacles to AI? And how do we make progress from here? So it looks, if you read the media, if you judge by how many millions venture capitalists are investing in AI companies, or how many billions companies like Google, Facebook, Microsoft, Baidu, everybody essentially are investing into AI R&D. you would think the problem is solved. It's not solved at all. There is very useful applications we can build out of AI today, certainly in image recognition and for transportation. There's a lot of excitement about better medical imaging system, so a medical image analysis system based on convolutional nets. There's already papers coming out of, take a picture of your skin with a cell phone and basically can tell you what kind of skin ailment you have. But it's not like we know how to solve AI. There's still a pipe dream. So what are the obstacles, really, to kind of making real progress in AI? Machines need to be able to learn and understand how the world works. And currently, they don't. They don't have common sense. So there's a lot of deep learning techniques that are applied to text understanding, to translation. So all the translation systems that have been deployed by Facebook and Google in the last few months use neural nets. They're based on neural nets. They're based on deep learning. Some of them use convolutional nets. Most of them use what's called recurrent nets. Some of them use a combination. But basically, we need machines to understand how the world works, the physical world, the digital world, how people work, things like that. And they need to acquire some level of common sense. So if you think about what's required for an intelligent system, you need a system to be able to perceive, to kind of get an estimate of the state of the world. You need the machine to remember. You need a machine to plan and reason. But one of the most important characteristics is that you need a machine to be able to predict. And I would say that, I would claim that the essence of intelligence is the ability to predict. The smarter you are, the better at predicting you are. It's not the only thing you need to be able to do, but it's a very important one. So I just mentioned common sense. What does that mean, really? What is common sense? So here is an example of that, still completely flummoxed most AI systems, all AI systems that we know of. A simple sentence called a Winograd schema. So Winograd is, a grand old father of AI, more classical logic-based AI. And he came up with sentences of this type: the trophy doesn't fit in the suitcase because it's too large, or the trophy doesn't fit in the suitcase because it's too small. So in the first form, you know that the it refers to the trophy. And in the second form, you know that the it refers to the suitcase. And the reason you know this is that you know the physical constraints of the world. You know what those objects are supposed to do. And so that's how you can sort of lift the ambiguity about what the it refers to. And there is my colleague at NYU, Ernie Davis, has made a list of 150 of those things. There are data sets that people measure the performance of AI systems on this, and the best AI systems get maybe 60-ish, 65% correct. Humans are above 95. Here's another example. If I say Marcus picked up his bag and left the room. This is not a suggestion, by the way. Even if you don't know Marcus, even if you don't know what room I'm talking about or what shape his bag takes, just with these few words, you can imagine a sequence of events that has to occur. Your common sense is filling in the blanks that are left open by this text, but because you know the physical constraints of the world, you know that Marcus is probably going to stand up and extend his arm and close his hand around the handle of his bag, and then it's probably going to walk towards the door, open the door, etc. Is very likely not going to attract his bag through telekinesis. Is not going to dematerialize like this dude here. Oh, it's not playing. To get out of the room, he's not going to fly to the door. He's not going to go right through the door. He's going to open it. So there's a lot of things you can infer because there's millions and millions of facts of this type that you can infer because you know the constraints of the world. That's what machines don't have. They don't have enough knowledge about the constraints of the world to kind of have this kind of common sense, and therefore they can't fill in the blanks. And that's what really annoying. That's what makes it really annoying to talk to a computer, basically. So common sense is really the ability to fill in the blanks. It's the ability to infer the state of the world from partial information, from perception, to infer the future from the past and the present, which is really necessary for planning, to infer past events from the present state of the world. And we do this all the time. It's, in fact, so automatic that we don't even realize we're doing it. Every one of us has a kind of a blind spot in your retina, which is where the optical nerve punches through your retina to get to your brain. So there's one area in your visual field where you don't see anything. And it doesn't feel like we don't see anything in this location. You actually have to design an experiment to realize you can't see there. And it's because our brain sort of fills in the blanks. Kind of infer what's in that location in the image. If you only see my left profile, you can pretty much infer what I look like on the other side, because you know that most faces are more or less symmetric. So there's a lot of things like this that we rely on, like a lot of, we've figured out the dependencies of a lot of variables, and that's what gives us common sense. So predicting whatever you don't know from whatever you know is predictive learning, or learning to predict, I guess, is predictive learning. And in my opinion, that's the key to making significant progress in AI. So this predictive learning is unsupervised in the sense that you would like the machine to be trained by just observing the world, the way essentially children and animals train themselves, right? There's a lot of concepts that we learn as babies that we don't realize we've learned because they're kind of subconscious. But there's a lot of concepts about the world that we learn when we're babies. Like we learn that the world is three-dimensional. We learn that there are independent objects that can move in front of each other. From parallax, we have two eyes and we can move our head. We learn object permanence. So we learn that when an object is hidden behind another, some of you can see this bottle now. You know the bottle is still there. That's object permanence. Babies learn this after a few months of life. You learn also that an object that's not supported is going to fall. Babies learn this between the age of 6 and 8 months. So all of those things that we take for granted, we all learn them. And we'd like machines to learn this as well. And so there's a couple justification for the necessity of learning through unsupervised learning, which means learning from data that just comes to us from the world without being labeled by teachers or humans. And one argument is that the number of samples that are required to train a large learning machine for any task depends on the amount of information that we ask the machine to predict. And so Jeff Hinton has an argument that says the brain has about 10 to the 14 synapses, and we live for only about 10 to the 9 seconds. So we have a lot more parameters than data. So this motivates the idea that we must do a lot of unsupervised learning, since the perceptual input, including proprioception, is the only place where we can get 10 to the 5 dimensions of constraints per second. That's a huge argument for unsupervised learning. We don't get enough information through language. We don't get enough information through or teachers. We get a huge amount of information from our environment by just observing. So I came to this slightly obnoxious slide. It's obnoxious to people who work on reinforcement learning. So there are three types of learning really in learning theory or machine learning. One is called reinforcement learning. So reinforcement learning is kind of like similar to when you train a pet or a circus animal. You wait for the animal to do the right action, and then you reward it. Okay? It's very inefficient. It requires lots of trials, because if the space of possible actions is very large, then there's a good chance the animal is never going to take a very long time before figuring out what the right action is. And so it's very inefficient. It works in certain situations. So for example, for games, it works really well to train a system to play games, like Go, for example, or chess or things of that type. And the reason is that you can have many copies of the machine play against itself millions and millions of games, and eventually figure out what the right policy is. This was very successful for checkers in the 50s. There's a famous work by Samuel from IBM. In the 90s, there was a very successful series of work by Jerry Tesoro, also from IBM, where he had a kind of grandmaster-level backgammon player using reinforcement learning and neural nets. And more recently, of course, you heard about DeepMind's AlphaGo system, which used a convolutional net applied to a Go board, trained with a combination of imitation learning on recorded games by grandmasters, and then fine-tuned by playing against itself millions and millions of games. And it's pretty much unbeatable nowadays. So reinforcement learning works in games. It works in certain situations for like search ranking and things like that, ad ranking. But it doesn't really work in the real world when you have sort of physical constraints. And the main problem, the main reason for this is that you can't have many, many trials in the real world. The main problem with the real world is that you cannot run it faster than real time. Maybe thankfully. So supervised learning, we talked about it. You give more information to the machine, you feed it the correct answer. And then unsupervised learning, there's a huge amount of information you feed to the machine, but it's unreliable information. It's, I'm putting this bottle here in my hand. I'm going to let it go. What's going to happen? It's going to fall. So you can predict it's going to fall. You probably cannot predict which side. So we get a huge amount of information from the environment by just observing it. And so that led me to this analogy that if intelligence is a cake, in this case a Black Forest cake, the bulk of the cake is unsupervised learning, the icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. And this has become a running joke in the machine learning community now. There's a lot of talks that have various versions of this cake, some of them with lots of cherries on top. But reinforcement learning works for games. That's what I mentioned earlier. This is a system to play Doom that was built at Facebook by a gentleman called Yang Tian, who is a research scientist at Facebook AI Research in California. It turns out there is a yearly competition of this, and he won it with his system. I mean, his system won it. So that's, again, pure reinforcement learning. Another problem we're attacking at Facebook is slightly more complex games like StarCraft. So StarCraft is sort of a combination strategy. It's a real-time strategy game, and there is real-time battles, but you have to also build all kinds of stuff. So it's completely unsolved. It's very, very challenging. It's something that both Google and Facebook are working on, and several other people, and trying to figure out if it's solvable at all at the moment. This is a very simple system that was trying to just do local, very simple battles. But here is an idea that goes back many years ago by Rich Sutton, who is sort of one of the founding fathers of reinforcement learning. And he was proposing an architecture called DINA, Integrated Architecture for Learning, Planning, and Reacting. And there's a quote from him here that says, the main idea of DINA is that the old common sense idea that planning is trying things in your head using an internal model of the world. This suggests the existence of a more primitive process for trying things not in your head, but through direct interaction with the world. Reinforcement learning is the name we use for this more primitive, direct kind of training. And DINA is the extension of reinforcement learning to include a learned world model. So basically, that's the idea that, and in fact, it's very classical in control theory, that when you want to control a plant, or the standard word that control theory is used for this, you have a model of the plant, the system you want to control, and you use this model as a simulator to kind of see what the effect of the sequence of commands will produce. And that's how you do planning. That's how robot planning is done, for example. But in the context of learning, you need to learn the model. Control theory is called that system identification. And you also need to learn the controller to figure out the good sequence of commands. So it's an old idea and very classical in some ways. But it's only making inroads in machine learning and AI, fairly recently. So what is the architecture of an intelligent system? And this is really sort of inspired a little bit by how the brain is structured. You have the world, and you have an agent, an intelligent agent. The intelligent agent produces actions that influence the world, and the world produces percepts that are interpreted by the agent, and the loop is complete. The agent inside of itself, here it's outside, but it should be inside really, has an objective, and it tries to kind of take the actions on the world that will put it in a state that will minimize its objective. Think of the objective as a cost, not as happiness. Think of it as unhappiness or something. So it wants to minimize the value of the objective over the long run. And if you want the agent to be able to do a good job at this, do this intelligently, inside of itself, it has to have a world simulator that is going to allow it to predict what's going to happen as a consequence of its actions, or just what's going to happen because the world is being the world. So that's this world simulator. to initialize the simulator, you need a perceptual system that estimates the state of the world well enough so that the simulator can be run accurately. And then you have a module called an actor that produces action proposals to the simulator to kind of run it forward. And a critic is a trainable system that predicts the expected long-term value of the objective. So the critic tries to kind of predict in the long run, if I take this action, what's going to happen to me? Is it going to be good or bad? If I want to become a little philosophical, a lot of emotions that we interpret as emotions are basically anticipations of things that will happen, whether they're good or bad. Like fear, for example, is the result of predicting that something really bad is likely to happen. And you have this prediction, and you kind of try to figure out what to do. Elation is the anticipation of something good about to happen. So that's the idea of model-based reinforcement learning. And we know how to build a critic. We know how to build the actor, pretty much. What we don't know how to do is build a world simulator. Or we don't know how to train it, really. We know how to do the perception side, I showed you earlier. How do we learn forward models of the world? How do we learn predictive models of the world? So there is a small experiment that was done at Facebook a couple of years ago by Adam Lehrer, Sam Gross, and Rob Fergus, where they took a 3D game engine as kind of a virtual world, if you want, and plugged a convolutional net on it and asked the convolutional net to predict what's going to happen. Where are those blocks going to fall? Are they going to fall? By just observing what happens when you run the simulation. And this is the kind of prediction that occurs. So you see the initial condition on the left. At the top band of 4 images is what actually happens in this virtual world, and below is a row of predictions at various times in the future. And you see that the system kind of does a fairly decent job at predicting what's going to happen, except in some cases where it's not clear how to predict, the predictions are fuzzy. And it's because there are several ways things could fall, and the best thing that the machine can do is kind of predict an average of all the various things that could happen. I'll come back to this kind of problem in a minute. But before that, I'll talk about why you would need a model of the world for another reason, for understanding text and answering questions, having common sense about events given to you by text. And there is a series of work which I think is extremely interesting in the context of deep learning, which is the idea of using neural nets that are augmented by a short-term memory. So it turns out neural nets are very bad at remembering things. You can train them to perform a task, but they basically don't have memory. So there are recurrent nets, so networks that have loops, and those have reverberating states and stuff like that that kind of give them a little bit of memory. But it turns out this memory is terrible. So even recurrent nets can't remember things for more than a few iterations. So there's been this idea that's been floating around for a couple of years now of or became more popular over the last few years, of augmented recurrent networks with a memory. There is roots of this idea in a very popular architecture called long short-term memory, LSTM, which is a type of recurrent net proposed by Ohrheiter and Spielhuber in the late 90s. And more recently, there's work at Facebook by Weston et al., and by Julien Nikolov, and work at DeepMind on neural Turing machine and what's generally called differentiable computing or differentiable neural computers. So you basically build a computer out of differentiable parts, if you want, which means now you can train the computer to run a particular algorithm by gradient descent. It's a very kind of interesting area to explore at the moment. And so here is what a differentiable memory looks like. The memory module in one of those recurrent nets is basically an associative memory. And so an address comes in, it's a vector. You compute the dot product of this vector with a bunch of keys. And then you pass the output of those to what physicists in the room will recognize as a Gibbs distribution. This is the formula on the left. Basically, it takes all the outputs that come out that you can interpret as energies, and it takes the exponential and normalizes them. So what you get on the output is a bunch of coefficients that are between 0 and 1 and sum to 1. And you use them to multiply the values, which themselves are vectors. What you get on the output of the memory is the weighted sum of those vectors weighted by those coefficients coming out of the input. So if the address exactly matches one of the vectors and the other ones are orthogonal to it, then one of those values is going to be 1, the other one 0. After the softmax is going to be a little soft, but that's OK. And then at the output, you will get the vector that has been indexed by this address. But the thing is, all the operations there are soft and differentiable, and so you can backpropagate gradient to that. So people have done pretty amazing things with memory augmented networks of various kinds, like you can have a machine read a small text, like this 15-sentence text, which is kind of a 15-sentence version of Lord of the Rings. Bilbo traveled to the cave, Gollum dropped the ring, blah, blah, blah. And at the end, you can ask questions. Where is the ring? Where is Bilbo? Etc. And the machine can answer. And what it does is that it stores each of the statements in its memory. And then it's been trained to kind of produce with pairs of questions and answers. And it's trained itself to access the relevant memory locations to answer particular questions. And so then you can ask questions. It's never been trained on Lord of the Rings. It's been trained on kind of other kinds of stories with people moving around and carrying things, which is really what the Lord of the Rings is all about. So my friends at Facebook came up with a categorization of about 20 types of questions that you might want to ask a machine, some of which involve simple inferences like, Brian is a lion, Julius is a lion, Julius is white, Bernard is green, what color is Brian? So if you assume that all lions are white, then you can answer that. And so there's 20 types of questions, and until now we had systems based on memory augmented network that could essentially solve 19 types of out of 20 of those questions. But this new system that we call entity recurrent net actually can solve all 20, and it's the first time the first system of its type that can do all 20 of those so-called baby tasks. It's basically a bank. I'm not going to go into the details of it, but it's basically a bank of recurrent nets that all take an input, which is a simple sentence like John goes to the kitchen. Okay, so the sentence John goes to the kitchen is encoded into a vector, and then it goes into each of those memory cells, and each memory cell has a gating mechanism that has it decide whether the information is relevant to it. And so you could imagine having a memory cell for the location of where John is and another memory cell for the content of the kitchen. And the system would update both of them when it sees a sentence of the type John goes to the kitchen. And the magic thing about this is that you don't need to tell the system that what the memory cell should do. You just have it read a text, and then at the end ask a question and give it the answer. And it kind of figures out how to infer the state of the world from all the sentences it gets. So it kind of learns how to maintain a current state of the world as the sentences that describe events come in. So it's a bit of a predictive model, estimating the state of the world from simple sentences. Okay, let me switch gear a bit and talk about the more general problem of unsupervised learning. So unsupervised learning really is discovering the structure of the world. And what that means is figuring out dependencies between variables in the world. So if your world consists of two variables, okay, let's imagine both of your eyes only have 1 pixel each, okay? So your entire visual world is 2 pixels. And your entire universe is composed of percepts that are those black dots, and they distribute in those two variables in that way. There is obviously a dependency between y1 and y2. If I give you the value of y1, you can predict more or less what the value of y2 would be with some uncertainty. The converse is true as well. If you give you the value of y2, you can sort of infer the possible values for y1. So how do we represent the fact that a machine should learn this kind of dependency, not knowing in advance whether we need to predict y1 from y2 or y2 from y1? And the answer to this is basically comes from physics, or from mathematics, implicit functions, or from physics, energy functions. We learn energy functions. So basically what the machine needs to learn is an energy function, a contrast function, let's call it an energy, that gives you low values on points that you observe and higher values everywhere else. Okay? So we need to come up with a neural net of some kind which will have parameters, and we'll adjust the parameters of the machine so that when it sees a data point from the world, it's going to make its output as low as it can. And then for everything else, it's going to produce a higher value. Okay? It's a function with many inputs, an image, let's say, and a single output, the energy. So that's what the learning process should look like, something like this, where the surface kind of evolves as the system is being trained. So the big question there is, it's easy to make the function produce low values for things it observes, but the question is, how do we make it take higher values outside for things it doesn't observe? So one technique is to pick a good set of points, contrastive points if you want, and then push up their energy. So change the parameters of that function so that its output goes up. And that's kind of what's going on here in this little animation. In fact, there is sort of 8 different ways to do this. There's 7, which I'm just going to flash but not talk about. And then skip to the 8th ones, which I think is probably the most exciting idea in machine learning in the last 10 years. I'm allowed to do this because I didn't come up with it, unfortunately. This is an idea that came out of Yoshua Bengio's lab at University of Montreal a couple of years ago by his former student now, Ian Goodfellow, and it's called adversarial training. And it solves the problem of predicting under uncertainty. So here is a scenario where I'd like to train a machine to predict the future. So I have what's called a generator, g of x. X is the past. Z is a source of random vectors, let's say. And y is a prediction for the state of the world, half a second later, let's say. Okay? And what I train the system with is many videos of me putting a pen on the table and letting it go. And of course, every time the pen falls, but every time it falls in a different direction. So there is a sort of a manifold, or at least a set, of plausible futures, which you observe in all those training videos where you see the pen falling in all situations, in all orientations. In fact, this manifold is actually a closed surface. It's topologically identical to a circle, okay, which I didn't do right here. So if you train the predictor in kind of a supervised mode where you tell it, here is the correct answer, predict that, here is the correct answer, predict that, it's going to get a lot of inconsistent desired output, and the best thing you can do is predict the average of all of those, which is basically a transparent version of this pen in all possible positions around the circle. And it's not a good prediction. It's not on the manifold. It's the average of the points on the manifold. So how do we do this? What we need to do is train the machine in such a way that when it makes a wrong prediction, but it's a prediction that happens to be on the right manifold, we don't punish it for it. We said, okay, you didn't predict that the pen fell in the right direction, but you actually did predict that the pen was going to fall. So you're not wrong, technically. The problem, of course, is that we don't know how to characterize this set. And so the trick in adversarial training is we're going to train a second neural net to learn to tell us if the prediction is on the manifold or outside. And that's very much like the problem I just mentioned of learning an energy function, learning a contrast function that distinguishes things that actually occur from things that don't occur. So that's the basic process is the following. You have the discriminator. So the discriminator is the one that computes this energy function. It takes a prediction. It takes the past frames, and it takes a prediction from the predictor, and it assesses whether this prediction is good. And the way the discriminator trains itself is that it takes an actual realization from the world, and it trains itself to produce a low value. These are the blue beads. And then when it gets a prediction from the generator, it assumes it's wrong. It assumes it's outside of the correct set of prediction. And so these are the green points, and it moves up the value of the energy for those points. Okay? So after a couple iterations, you might end up with something like this, where the green points have kind of moved closer. And so the predictor has, so the discriminator has kind of figured out the difference between the two. That's where the energy comes from. But now the way you train the generator is that the generator trains itself to make predictions that the discriminator cannot tell are not real. And it can cheat because it knows the gradient of the output of the discriminator with respect to its input. And so it can adjust its internal parameters, so that it produces an output that will fool the discriminator into thinking it's real. So you have this interplay between those two networks that train against each other, which is why it's called adversarial training. There's a proof by one of my students, Michael Mathieu, which shows that It basically is akin to a Nash equilibrium in the end. So you're minimizing two functions with respect to the parameters of those two networks, and in the end, you kind of reach some sort of Nash equilibrium. So you can train things like this to do pretty amazing things, like generate images from scratch. So here, there is no past to predict from. You just give a bunch of random numbers to a neural net and have it generate an image, and you train it with images of bedrooms. And these are non-existing bedrooms generated by a neural net. They don't look like anything in the training set, but they look kind of like bedrooms. So the three authors are in different institutions. Sumit Chintala is a research engineer at Facebook. You can train it to interpolate between manga characters. You can do face arithmetic, so this is kind of fun. You can figure out what input vector, random vector, would produce a particular face by gradient descent. So you take a face and you figure out what input vector would have produced this face. And you do this for, say, 3 faces, a man with glasses, a man without glasses, and a woman without glasses. So you have those 3 vectors. When run through the network, they generate those 3 faces. And now you take the first vector minus the second vector plus the last vector, you generate through the network, and what you get is a woman with glasses. It's kind of amazing because that means, it's figured out that a man with glasses is to a man without glasses as a woman with glasses is to another woman without glasses. It's the same vector that links women with and without glasses as the vector that links men with and without glasses. This kind of an energy-based form of this, I talked about the Nash equilibrium, and I don't want to go into formulas, but it's sort of an energy-based form of adversarial training, the one I described to you, and this is trained on 1 million natural images from the ImageNet dataset. And if you're in the back of the room, you kind of squint and you kind of look at those pictures and you say, oh, they look nice, they look natural. If you're on the front row, you're saying, what the hell is this? It's like there's no recognizable objects. They all look kind of object-like, but there's nothing you can recognize here, right? This is like weird-looking kind of, this dude here. It's like a fast train with a sail and with kind of an airplane wing on top of this ocean. I mean, it's like, everything is kind of mashed together. So it's figured out the low-level statistics of images, but not really quite the kind of global structure of it. This is what happens when you train on dogs. You get kind of soft dogs. Salvador Dali dogs, And here's what happens when you do video prediction. So at the top right is video prediction when you train a system, a fairly large convolutional net to predict using a least square loss, essentially. Predict the next frame with least squared error. And the other 6 are the predictions you get when you train with this adversarial training criterion. So the first 4 frames of every animation is observed, is real video, and then the last 2, which are circled in red, are predictions. And it kind of extrapolates pretty well what's going on, more or less. This is the same system. I'm going to show you the second one, actually. Same system trained on videos taken by a camera kind of moving around in apartments in New York. And so what the system has to do now is predicting 5 frames in the future. Again, the predicted one that's circled in red. Look at this guy. So this is kind of a bookcase. It's kind of like a library. And it has to dream up what the library looks like. And the rest, there's another bookcase here, which is dreaming up as well. So it sort of invents what the rest of the apartment should look like as the camera turns. So that's 5 frames, and that's 50 frames. And that's where you realize that we haven't solved the problem because things go to hell after a few frames. Okay, I think I'm going to stop here and take some questions, and thank you for your attention.
I don't know about you, but I could have stayed for the rest of the day. Thanks very much, Yann. So, okay, questions. We'll take as many as he can stomach. And then actually lunch is going to be a limiting function at some point. The stomach will come into it. So off you go, Al. Oh, you need a mic, and then I apparently have to repeat it so that we can hear it on the camera.
First, thank you for a wonderful talk.
Thank you.
One of the questions that intrigues me is, do you think we'll ever be able to write a computer program to simulate human consciousness? And if so, is this the path to it?
Okay, diving right into the philosophical questions, huh?
So I'll repeat it. Al wanted to know if we can ever write a program that will simulate human consciousness, and the answer is?
The answer is, I actually don't know what consciousness is.
You don't know what consciousness is?
No, it's not a well-defined concept. So, some people, it's not entirely clear whether consciousness is anything more than kind of a model of yourself. So, I was talking about predictive models, and included in the predictive model of the world, you have to include yourself. Because you have an agency in the world, and so if you want to predict what's going to happen in the world, you kind of have to include yourself as part of the world. And so perhaps you need the fact that you have kind of a part of your brain kind of looking at another part of your brain acting as if it's you. Maybe that's what consciousness is. But I'm sure if I say this, if there were philosophers in the room, they would kind of take their guns. There is, there's other.
But Yann, if it were that,
yes.
You would say yes.
If it were that, I would say yes, but I don't know if it's that. Yeah. So it could be also that consciousness is just a side effect of being smart. Because you have good models, you kind of include your own actions as.
I need to follow up on this. Whenever I have an operation that requires anesthesia, I ask the anesthesiologist, how does the anesthetic work? And his response is, I have no idea, but I know what it's going to do to you when I inject you with it. So from a pragmatic point of view, there's something that an anesthetic does to you to eliminate what at least part of me thinks of as consciousness.
Yeah, I mean, certainly you don't have any conscience of time once you are under complete anesthesia. And it's not just your consciousness that's shut down. A lot of things are shut down. A lot of systems are shut down. Your frontal cortex, has a lot of the decision making, and your prefrontal cortex does a lot of this prediction, world model type things. All of that is turned off. But I don't view this. I always wonder if this is a real question, in the sense that back in the 17th century, when people discovered how the eye was working, they figured that it's a lens, and then the image forms in the back of the eye on the retina, and it forms upside down, and people could not fathom how it is that we see right side up, right? Because the image is upside down. And now we realize that question doesn't make any sense, and so it could be that consciousness has this kind of flavor that the question doesn't make any sense, but I don't know.
So I have to ask mine now. Empathy, same thing.
Yeah.
Is empathy a function I can transfer because it's actually, or that I can emulate, I should say, because it's something that is actually my model of me trying to model to a view of that's not me but related to me, but similarly is sort of a background function running.
Right. So empathy has to be built into this objective function I was talking about. Right. In the architecture of the intelligent system, you have the world model, the actor, and the critic. And the critic is a predictor for the ultimate objective function. And to make you want to care about other people, this has to be built into your objective function. This is not going to come naturally. There's a lot of animals who don't have this at all because they're not social animals. They don't care about empathy. There's a whole bunch of species that basically eat their mate right after sex, right? So it's for the survival of the species.
Maybe in France.
Huh? Octopus, for example.
Yeah,
octopus is very smart, but very often one of the partners don't survive. And then the mother, as soon as the mother lays their eggs, she dies. And so, empathy is a notion that's proper to social animals. And I think if it's implemented somewhere, it's in this hardwired objective function we have at the bottom of our brain.
And you said sociopaths clearly just miss that function for whatever reason, whether it's environmental growing up or not, and that's the problem.
Right. So there is this interesting discussion we had yesterday at dinner where, those three modules, the world model, the actor, and the critic, and the objective function, there's a lot of sort of human, failings of human character that are due to kind of inaccurate versions or bad versions of each of those three modules, right? So you can have a bad world model, makes you kind of stupid because you can't really predict what's going to happen as a consequence of your actions. You can have a bad objective function, which kind of makes you evil, possibly. And then you can have a bad action generator, which means that even though you can predict, even though you want to do the right thing, you can't figure out how to get there, okay? And then there are, some people for which like all three of those things are wrong, and sometimes we elect them to official.
We'll draw a veil over that one. I think we have one good example of that. So off we go.
The question I have is, recently they applied, a game learning program to the game of Go. Now, Go does not succumb to brute force techniques like for chess, and I think they use some kind of deep learning technique.
Yeah.
And recursively playing itself until it got better and better.
Right.
Would you say something about those algorithms and how they're related to what you covered?
Yeah, I said just a few words about this earlier, but so basically there's 2 or 3 phases of training of this system, and kind of 2 different neural nets inside. So there is one neural net, it's a convolutional net, very similar to the one we use for image recognition, that takes the Go board, which is, you can think of it as a 19 by 19 image with 3 possible values for each pixel. Okay, so it's a very simple image in a way. And then you have this convolutional net that's plugged on it, and that convolutional net is trained, supervised, on a catalog of recorded games between masters. Okay, there's thousands and thousands of those games around. In fact, I think a few million. And so you do the same kind of training that the NVIDIA people use for the car. You show a Go position, and you train the system to predict what would be the move. In this recorded game, train the system to predict the next move, essentially. So that's the first phase. If you train the system to do this, it plays, there's a number of teams that have done this at the same time, more or less, as DeepMind. And you get a system that performs at a level of about 2 dans or so, okay? Which is actually good, it would beat me. I'm terrible, so of course that doesn't mean anything. Then there is a second, kind of a second component, which is what's called Monte Carlo tree search, MCTS. So this is a classical technique that Go playing machine used to use before AlphaGo, and that's basically a sort of arborescent search, kind of similar to what's used in chess, except it's kind of Monte Carlo sampling. So instead of exploring the entire tree, you kind of sample parts of the tree in sort of various ways. Because the branching factor is so large, you can't possibly do the exhaustive one. And so you do that, and what you can do with this is that you can fine-tune you can train an objective function, another neural net, to predict whether a particular position is going to be a winning position or not. Okay? And you don't have to actually train this, you can just use MCTS with the predictor to have a pretty good player. So there's a couple of Go players that use supervised pre-training plus MCTS, and the best ones play at a level of about 6 dans, 6 or 7 dans amateur, which is quite good. It's among the best Go programs in the world before AlphaGo. There's a system out of Facebook, actually, that works exactly this way. The additional ingredient that AlphaGo from DeepMind has is this reinforcement learning procedure. So it trains a second neural net to evaluate whether a position is a winning position or not. And the way it trains that is by playing lots and lots and lots of games against itself using the combination of convolutional net plus MCTS, and then eventually kind of adding the trained strategy with reinforcement learning. And the more this thing trains, the better it is. And now it's several dan clicks above the best human players.
So next question.
One of the things that baby has is arms and legs and feels the real world. Do we need to include those kinds of inputs as we go forward with artificial intelligence? Yeah,
that's a good question that I don't think has a clear answer yet. So there are experiments that seem to show that certain animals need to act in the world to be able to learn. There's an experiment that was done a long time ago where you you put a baby cat on a kind of a carousel, and and another baby cat on the other side of the carousel. And the first cat can kind of walk around and move the carousel, and the second one can just watch. And the second one doesn't develop normally. So this seems to suggest that for cats to develop normally, they have to be able to act in the world. But there could be all kinds of other artifacts of the experiment. It's not entirely clear for machines whether there is a need for action. Certainly, action allows us to kind of ask questions to the world, right? If you are just observing the world, then the world has to be curated to some extent so that you see the things that are important. Because if you don't do anything, most of the things you observe are very boring, right? So if you are kind of just sitting in a room and not doing anything, I don't think you're going to learn very much. But if you watch YouTube video all days, maybe you'll learn something about the world. I don't know. It's possible.
That's interesting, because I tend to think you do need that sensory input, but you would say it's possible that you could watch the act of someone touching and not have to touch.
Possibly.
Yeah.
Possibly.
Okay, other questions?
So this is obviously a dual use.
You need to wait for the mic, John.
Obviously, like many things of physics and else, there's dual uses to this. Can you just comment? I mean, obviously, we're all really excited by this, but we all, in the back of our minds, think about the military consequences of this. So how are we going to handle that? I mean, I'm just asking naively.
Well, Minority Report, future crime, right? That is premised on a similar idea.
Yeah, there are a few startup companies in various countries that, thankfully not so much in the US, although there are a few of those, that try to do things like predict recidivism or horrible things like tell if a person is likely to be a terrorist just by their face. I mean, this is basically automated racial profiling. And so a lot of us in the community became kind of very annoyed by things like this, and not just because it gives a bad name to the technology, but because it's ethically wrong, and someone has to say that. And at this time, the people who are informed about what the technology can do are us. And so I was instrumental in forming something called the Partnership for AI, which is a sort of industry group. It's not just industry, but it's funded by industry. So the founding companies are Facebook, Google, Amazon, IBM, and Microsoft, and then Apple also joined as a founding member. And there's a board formed by representatives from those companies, as well as people from the ACLU, the IEEE, a lot of non-NGOs, essentially, that worry about ethics, economic impact, and things like that. So the economist on the board is a guy called Jason Furman, who was the director of the Council of Economic Advisor for the Obama administration. So there's a very sort of deep reflection among some governments, certainly the Obama administration, while it was still there, that produced a report late last year about the potential impact of AI and how our governments would need to kind of deal with this problem and perhaps encourage it. And it's probably being ignored by the current one. It's being very widely read outside of the US. There's a lot of governments who are thinking about this as well. But I think we as technologists need to kind of come up with guidelines for proper use of this kind of technology. We're not going to be able to stop the military from using it, but there are, perhaps safety guidelines that we should tell them. So none of us is really, at least I'm not, worried about a Terminator scenario. It's more like misuse and sort of, short-term ethical problems.
Couple more questions. Mark, yeah.
Yann, I have another applied question. Today, especially in social networking and media, there's a lot of talk about and discussion of alternative facts, almost the alternative reality.
Right.
How can these techniques be applied to that, or is work already underway?
There is work underway to apply machine learning, and today machine learning to a large extent means deep learning, neural nets, etc. So there's quite a lot of work, at Facebook and Google, various other companies, on sort of identifying the, potential reliability or unreliability of a piece of news. And it's not just, you can't do this just based on content. You have to kind of correlate that content with other stories on the same topic from sources that you might trust. And then there is an issue of how you design the product so that people will believe in the predictions that are done by the system. and trust them, because maybe half the population believes the New York Times is a reliable source of information, but there's a half of the population in the US that believe it's fake news. So how do you kind of design a system so that the indication of reliability are done properly? So Facebook is actually rolling out, as we speak, in France and Germany, 2 systems to kind of identify fake news. There's a little bit of automation in it, but it mostly relies on sort of traditional media to kind of help assess the reliability of news. And the reason why it's deployed in France and Germany is because they have upcoming elections that they really would like external countries not to interfere with, and they sort of come to the realization it could be a big problem for them because of the same issues there is in the US.
So related to that one, though, I think one of the problems in that is there will be another deep learning network that proves that is wrong for those who want to believe that. So what we have to then have is that I think it gets back to the empathy function, where we have to actually somehow find a way of saying, regardless of what you believe, you should have a world model that incorporates that other view, and then you can behave better.
Right.
Because I think the newsy part is a symptom, but not the cause. Then we need to go after the cause part. Would you agree or not?
Yeah, it's a very difficult issue that has more to do today with product design, I would say, or user interface than it has with technology, really. I mean, certainly technology is going to help more and more with these questions, but I think it's more how you get this. I mean, this is really not my specialty, I have to admit. I'm a research scientist. Most of the research we do is, open research, and we work with public data. We don't actually work that much with Facebook data. So this is actually taken care of by other people within the company.
2 more. These will be the last 2, I think, and then we'll have to wrap up. Otherwise, we're favoring people at the back. It's Eve back there, isn't it? They've been patient, so Eve, off you go.
Yeah. Just a curiosity. You mentioned that we have 10 to the 14 synapses in our brain. Now, our brain only consumes a couple watt, I would assume. So how power efficient are your current systems compared to the human brain? Because if you want to have these systems everywhere, obviously they need to be at least within a couple orders of magnitude. So how efficient are they, and what are people doing to make them more efficient?
It's terrible. It's horrible. It's terrible for various reasons. It's terrible. So to give you an idea, a typical GPU card, which is kind of, in terms of numerical computation, maybe as efficient as it gets, is about 10 teraflops, and it's about 200 watts. So, the brain is roughly, if you really want to make a kind of global estimate of how many operations you need in the brain to kind of get a functioning brain, that's about 10 to the 17 operations per second. It's a lot of teraflops. It's 100,000 teraflops. And that's 25 watts in the brain. So there is, at least 6 orders of magnitude difference between, white source and GPUs. Now, a lot of that can be bridged with, just the progress of technology, in the sense that GPUs are very, very far from being the kind of, optimal things to do to run neural nets. So if you want to run a neural net without training it, just in operation, you don't actually need that much accuracy in the computation. You don't need 32-bit floating point. You can get away with just a few bits on the weights and the states. In fact, there were chips of this type that were built in the department I was in at Homedale in the early 90s. There's a chip called ANA, which means Analog Neural Network Accelerator, and it was capable of 4 billion operations per second, where an operation was a multiply-add, essentially. And the states in this neural net, so it was a convolutional net accelerator, basically. And it used 4 bits for the states of the units and 6 bits for the weights. And it was good enough to do character recognition. Probably not good enough for full-fledged image recognition, but you don't need much more than that. So reducing the precision gives you a huge win. Then kind of tailoring the architecture to run convolutional nets as opposed to run kind of general video rendering or whatever will give you another win, because what costs energy is not so much the computation itself, but it's moving data around. So if you can have data locally stored where the computation takes place, then you save a huge amount of energy, of power. So there's going to be a lot of progress, I think, over the next few years on this. There's quite a few startup companies and larger companies that are building, low power convolutional net accelerators, essentially chips for embedded applications. For mobile phones, for cars, for toys, for vacuum cleaners, lawn mowers, whatever, maintenance robots. You're going to have those vision chips everywhere within 5 years. That's my guess.
Do you think as the world model gets better, the agent can get smaller, or the objective function can be, well, objective function probably is not the largest part, right? But if the world model gets better, the agent can be simpler, and that then saves in computational power, I would imagine?
I'm not sure that would be a good way of saving computation. But I think now that people have a model for how to do perception, there is a lot of people interested in hardware who are kind of focusing a lot of energy on trying to make this efficient and cheap. And I have actually a bet that another bet of this type.
It's going to be a fancy dinner.
It's a fancy dinner with Larry Jackal. The bet was signed in 2013, and what I said was that by 2023, which is not that far in the future, your smartphone will have enough power to drive your car. So basically, the hardware may not be there, but the connection between the phone and the car may not be there. But in principle, you should be able to just hold your phone in front of you and have it drive your car. Now, of course, real self-driving cars will not use your cell phone, but it's kind of a statement of how technology will evolve.
Last one, and then I think we'll have to wrap up. Okay, we'll go back.
So this is maybe a little bit of the Terminator type thought, but when and what are your thoughts on how will AI reach a point where it begins to replicate itself, and will we be able to understand it, or how will we be able to control it?
Yeah, this is a question that some people in the business are kind of interested in. To me, it's a little abstract because we're not close. We're very, very far from having a technology to have intelligent systems. Self-replication requires something else, which is physical interaction with the world and kind of fabrication, all that stuff. So why would we give this kind of ability to robots? I mean, I think most of AI of the future will be virtual AI. It won't be robots. It'll be kind of intelligent virtual assistants you can talk to, things that kind of run the world basically, but not but don't have kind of much physical interaction with it. So that's point number one. There's quite a lot of people who are worried about kind of the theoretical aspects of controllability. So, for example, is it enough to construct a robot or an AI system with an objective function that is hardwired and sort of cryptographically protected, for example, so that the robot or the AI system cannot modify it? And so if it cannot modify its objective function, that means it has to abide by it. You can't self-modify it. And so in those objective functions, how do you design them so that there are kind of fences that prevent the system from doing bad things? So there's a book by a guy called Nick Bostrom. He's a philosopher at Oxford, and he wrote a book called Superintelligence. And by reading this book, that people like Elon Musk and Stephen Hawking and Bill Gates made those declarations that maybe AI will kill us and we have to be careful. And frankly, the scenarios that are described in this book, to me, are completely unrealistic. So there's a scenario, there's the so-called paperclip scenario, where you build a machine to build paperclip, and all it wants to do is optimize the maximized number of paperclips it produces, and it's super intelligent, so it kind of convinced everybody to not turn it off, and ends up turning the entire galaxy into paperclips. Or the solar system, or just the planet Earth, okay, that's enough. But I think we would have to be extremely stupid first and extremely unlucky for this to happen. It's hard enough to get a machine to work at all. So,
After this year, we're not so sure about that.
Yeah, right. No, I mean, do you give you put a child in front of a nuclear button? No. You don't give infinite power to things for which you don't have complete trust. Except presidents, maybe.
Okay, I think anyone else? Anyone else? The last bid for a question. Okay, yes, there you go. Last hand. Just wait for the microphone and then.
Thank you for your lecture. My question was, a lot of your examples were visually related. Do you see research for example, speech, stuff like that, translation from one language to another?
Yeah, so there's a lot of work on translation, there's a lot of work on natural language understanding, a lot of work on dialogue systems for virtual assistants. So that's kind of a big prize for a lot of companies that are involved in AI, which is how to build the underlying technology for useful virtual assistants. We're not talking about the current version of, Alexa, Google Home, or Siri, which are very scripted. There is only a certain number of questions they can answer, and if you go outside of that, they answer with a joke. And all of those kind of scenarios are scripted by humans. There's databases that can be accessed for the answers. There's not a huge amount of AI behind this, I have to admit. So the question is, when will we have machines that have enough background knowledge and common sense so that we will be able to talk to them and not be incredibly frustrated when we talk to them because they'll be sufficiently intelligent to understand what we mean. So Facebook has been running an experiment, which is sort of a bit of a Wizard of Oz type experiment. It's a project called M, and it's a intelligent virtual assistant. So you have on your phone, you communicate with it through Facebook Messenger, and you can ask it anything, even to kind of renegotiate your cable bill or something. And it's humans doing the job, which is why it's only available to about 10,000 people. But part of it is automated by kind of AI system that kind of figure out what kind of question it is and sort of produce an answer, and then it's kind of, more or less automated. So there's a certain percentage of those questions that can be automated. But the lesson from this project is that there is a very, very, very long tail of very complicated things that people want out of a virtual assistant for which the technology just doesn't exist yet. And it's going to take, decades, I'd say. At least one decade.
We should have a fancy dinner bet on that.
That's right.
With that, we will wrap up and thank Yann once again.
Thank you very much.
So I have to give Yann something. So before you leave, I have to give him what he came here for, which isn't you. No, of course it is in part. This is the Shannon Luminary Award that you are the second recipient of the year. And it's a trophy we've had specially created for this series. Wonderful. So well done. And it was a fabulous, fabulous lecture. It's been lovely having you here.
Thank you very much.